In an earlier lecture, we proved the strong law of large numbers, the first major limit theorem of probability theory. It says that if xn is a sequence of L1 independent, identically distributed random variables, then their empirical average converges almost surely to their common mean. We'd like to get some understanding of the rate of convergence in the strong law of large numbers. One clue came from a slightly stronger version under the assumption that the random variables are L2. This L2, strong law of large numbers, which says that if xn is a sequence of independent, not even necessarily identically distributed, L2 random variables with common mean, then if we take the sum of those random variables, center it, and divide it by some growing coefficient Bn, which diverges to infinity fast enough that the sum of the reciprocal squares of the Bn's is finite, then this renormalized sum tends to zero almost surely, and in fact also in L2. For example, if we take Bn equal to n, then of course 1 over Bn squared, 1 over n squared is a summable sequence, and so this reproduces the strong law of large numbers under the stronger assumption of L2 rather than L1 random variables. But we can do better than that. For example, if alpha is any coefficient strictly greater than 1/2, then the sum of 1 over n to the alpha squared is finite, since 2 alpha is strictly greater than 1. And that tells us that the centered sum, Sn circled, divided by n to the alpha converges to 0 almost surely, and in L2, and just for good measure, even in the weaker sense, of course, of weak convergence. So that says we can renormalize by a coefficient that grows any polynomial amount faster than the square root of n. But the square root of n itself gives us the harmonic series, which just barely diverges, and so we cannot conclude from this theorem that Sn over root n converges. And in fact, it doesn't. There's a phase transition that happens at alpha equal 1/2 here, and that leads to the next fundamental limit theorem of probability theory, the central limit theorem. In this first basic form, we'll state it, it says the following. If xn is a sequence of IID L2 random variables with common mean t and common variance sigma squared, then if we take the sum of the first n of those IID variables and standardize it, meaning we center it and divide it by not n but the square root of n times the common standard deviation, then that standardized sum converges not to a constant, but rather converges weakly to a standard normal random variable. And so taken together, this shows that as we decrease the coefficient here in the renormalization, this normalized sum concentrates on 0 until we reach alpha equal to 1/2, in which case it no longer concentrates on 0. It is now randomly spread out, always by this same universal noise profile. We already saw this theorem in action in the special case where the xn's were Rademacher random variables, having 2-point masses of equal weight at plus and minus 1. In fact, we're going to prove the general central limit theorem using the same method, which is to apply the continuity theorem. By the continuity theorem that we proved in the last lecture, in order to prove weak convergence, it's necessary and sufficient to prove that the characteristic function of the standardized sum converges pointwise to the characteristic function of the standard normal. Well, we know how characteristic functions behave under rescalings. We can put the scaling in with the variable instead of the random variable. The centered sum is just the sum of IID terms, and we know that the characteristic function of a sum of independent terms is the product of the characteristic functions. And so this gives us the nth power of the rescaled characteristic function of one of the centered random variables, say x1. Now, x1 is assumed to be an L2 random variable, which means that its second moment, which is the definition of the variance, is constantly equal to sigma squared. But that means that the characteristic function of that L2 random variable is a C2 function. For C2 functions, we have Taylor's theorem to second order, which tells us that we can expand this characteristic function in terms of its linear part with a remainder term that will be quadratic, and the coefficient will be 1/2 the second derivative of the function at some point that is not necessarily 0, but is between 0 and the evaluation point x. Now in particular, what that means is that if we take the limit as x goes to 0 of this evaluation point r of x, that, by the squeeze theorem, will be 0. Now, notice that phi, being a characteristic function, takes the value 1 at 0. As for its derivative, we know that the derivative, given that x1 circle has a first finite moment, is equal to the expectation of ix1 e to the I cx1 evaluated at c equals 0, which means this is 1, and so this is just I times the expected value of x1 centered, but x1 centered has expected value equal to 0. And so altogether, Taylor's theorem here tells us that this characteristic function takes the form 1 plus 1/2 the second derivative of the characteristic function, evaluated at a point r of x times x squared. But we're going to be evaluating this at the point x is equal to c over sigma times root n. And as n goes to infinity, that x tends to 0. And so r of x is going to tend to 0. Now, because of the finite second moment of the distribution x1, phi x1 double prime is a continuous function, and therefore we also have that this converges to phi double prime at 0. And as before, this term will just become 1. This gives us minus the second moment of the centered random variable, which is the negative of the variance of x1, which is negative sigma squared. And so putting all of this together and taking nth powers, we get that the limit that we're interested in is the same as the limit of 1 minus 1/2 sigma squared times c squared over sigma squared times n, all to the power n. Those sigma squareds cancel, and now we can use basic calculus to conclude that this, in the limit as n goes to infinity, is e to the minus c squared over 2, and therefore, by the continuity theorem, we have proved the central limit theorem. We're now going to spend some time considering generalizations of this theorem. One fairly straightforward one is to move from one dimension to d dimensions, that is, to consider a central limit theorem for random vectors rather than just random variables. In order to understand what that theorem will say, we need to be precise about what a multivariate normal distribution is. A multivariate normal distribution will be determined by a covariance matrix, which can be any positive semi-definite matrix. So let Q be such a matrix, which just means a symmetric matrix all of whose eigenvalues are non-negative. Equivalently, it's any matrix that can be written in the form A transpose for some other square matrix. A measure on RD is called a centered normal distribution of covariance Q, precisely if its characteristic function has this form here. If we've chosen a particular matrix A to be a quote-unquote square root of Q, then we could alternatively write this as follows, which makes it look more like a standard normal with standard deviation A. We denote this distribution normal of mean 0 and covariance Q. And it's an exercise for you on your next homework to show that an alternative description of this same distribution is to say that the random vector x has normal entries whose variances are the diagonal entries of the matrix Q, and so that the covariance between the I and j entries of the vector is the ij entry of the matrix Q. Another cute way of writing that in matrix notation is to say that the whole matrix Q is the expected value of the matrix x transpose, where here and in the sequel we will start to apply expectations to vectors and matrices just by having it apply component-wise. So the multivariate central limit theorem says the following. If xn is a sequence of random vectors in Rd, all of the vectors independent from each other and identically distributed, but that doesn't mean that the entries of each random vector are independent from each other. Instead, we assume that they all have common mean and common covariance, which we'll call Q. Then, because we don't necessarily want to try to divide by this matrix Q, which need not be strictly positive definite, the theorem is that if we take the standardized sum, 1 over the square root of n times the sum of the first n centered random vectors, that converges weakly to a random vector z whose distribution is normal of covariance Q. In the case d equals 1, this is the same as the central limit theorem that we proved on the previous slides, except that in that case we divided by the square root of Q here and got a 1 here. And you should easily be able to justify that that's equivalent to taking this standardized sum and getting a normal with the variance sigma squared over here. The main tool we'll use to prove this is a more general tool that we could have stated earlier, which relates weak convergence of random vectors to weak convergence of their components, and sometimes goes under the name the Cramér-Wold device, after Cramér, the same one we've seen before, and another Swedish econometrics colleague of his, Wold. The Cramér-Wold device says that a sequence xn of random vectors in Rd converges weakly to a random vector in Rd if and only if all possible linear combinations of the entries of xn converge to the appropriate linear combination of the entries of x. In other words, if and only if, for every vector xi in Rd, the random variable xi dotted with xn converges weakly to the random variable xi dotted with x. The proof of this is a straightforward application in 2 directions of the continuity theorem. For the forward direction, suppose we know that linear combinations of xn converge weakly to linear combinations of xi. Well then, the expected value of I xi dot xn converges weakly to the expected value of I xi dot x. That is a straightforward consequence of the continuous mapping theorem, since the function e to the I blah is a continuous function. Well, that means, by the definition of weak convergence, that I can take the expected value of any bounded continuous function f of this random variable for fixed xi, and it will converge to the expected value of that same function of e to the I xi x. Now, notice that e to the I xi dot xn is a random variable that takes values in the unit circle in the complex plane, which is a bounded set. And so all I have to do is take some function f that is continuous and bounded and has the property that it equals the identity function on the unit circle, or the unit ball, if we want, for good measure. We take a function that is the identity on that ball, and then outside of some bigger ball could shift down to 0 and even be compactly supported as long as it's still continuous. Well then, because these always take values in the unit ball, with that function f, this is just equal to the expected value of e to the I xi dot xn, and this is just equal to the same thing with x instead. But that is the characteristic function of xn at xi, that is the characteristic function of x at xi, and so we see that we have proved that we get convergence pointwise of the characteristic functions. And by the continuity theorem, it follows that xn converges weakly to x, as claimed. For the converse direction, if we already know we have that convergence, xn to x weakly, then if I fix any real number u, if I take the characteristic function for fixed xi of xi dot xn at u, that's equal to this quantity here, and I'll use the real linearity of the vector dot product to write this like that, u times xi being the vector that's involved. Since xn converges weakly to x, that means that for all vectors, including this one, this converges to the expected value of e to the I u xi dot x. But now I'll rewrite the brackets in the other order again and realize that this is just the characteristic function of xi dot x evaluated at u. And so that shows that for any real number u, the characteristic function of xi dot xn converges to the characteristic function of xi dot x at u, which by the continuity theorem implies that xi dot xn converges weakly to xi dot x, concluding the proof of this lemma. So that puts us in a good position to prove the multivariate central limit theorem, which I've restated here. So our goal here is to show that xn converges weakly to a random vector which has this distribution. By the Cramér-Wold device, that's equivalent to showing that if I take any vector xi, xi dotted with xn converges weakly to xi dotted with this vector z. Now, for such xi, let's denote xn xi to be this dot product. This is now a regular real-valued random variable. Because the xn random vectors are independent, these, which are functions of those random variables, are independent, and we can compute their characteristic functions using basically the same calculation we had on the previous page. This is the expected value of e to the I u xi dot xn, and we can put the u together with the xi to get the characteristic function of the random vector xn at u xi. The xn are identically distributed, and so that's the same thing as the characteristic function of x1 at u xi. And so that shows that the characteristic function doesn't depend at all on the index n, which shows that these xn xi are not only independent, but also identically distributed. They're also L2 random variables, and we can compute their mean and variance as follows. Again, utilizing the notation that the expected value of a vector is the vector whose components are the expected values of the entries. The expected value of xn dot xi is just, since xi is a constant vector, xi dotted with the expected value of xn, which is constant in n, so we'll just compare it to the first one. And the variance we can write in this nice form. It is the expected value of the square minus the square of the expected value, using the value that we computed above here. But now we'll use this nice trick that for any two vectors, the dot product squared, which can be written as v transpose w times v transpose w, could also be written as v transpose w times w transpose v. And we can write this using matrix notation as the dot product of v with a square matrix ww transpose, a rank 1 matrix, in the middle there. So if we apply that to this expression here, we get that, and we can similarly apply it to the second term to get that. Now, we note again that since the coefficients of xi are not random, we can pull them outside the expectation. And then we have xi dotted with the expected value of something minus xi dotted with some expected values. Combining terms and using linearity, we can rewrite this as xi dotted with this difference times xi. And now I leave it to you, following exactly the same computation that we did, giving the different formulations of what covariance is in an early lecture, to show that this is the same thing as the expected value of xn-centered times xn-centered transpose. But because of the identical distribution here, we can make those all ones, and that is, by our definition, right here, the matrix Q. So we see that the variance of the random variables xn xi is just constantly equal to xi dotted with q xi. Thus, we can now apply the basic central limit theorem that we proved earlier and see that if we divide by the square root of this variance times square root of n, the sum of the centered random variables, that converges weakly to a standard normal random variable. But as mentioned earlier, we can, of course, shift this constant over here instead and get that 1 over the square root of n times this sum is going to converge weakly to a normal that is centered, and it has variance equal to xi dotted with q xi. Now, by definition, this xj(xc) is just xc dotted with the random vector xj. And so using linearity of the sum and the dot product, that's just xc dotted with the standardized sum of the xj's. And so what we've proved is that that converges to a normal of variance qxc dotted with xc. And as part of your homework, you're checking that that is the same in distribution as xc dotted with a random vector whose distribution is a multivariate Gaussian of covariance q. And so since that calculation holds for all vectors xc, it follows from the Cramér-Wold device that this multivariate central limit theorem holds. Now we're going to proceed from here to tackle more general versions of the central limit theorem in one dimension, where we'd like to weaken the conditions, the identical distribution, maybe even the independence and the formulation of the theorem, to see how we can prove lots of structures are asymptotically Gaussian, even if there is some mild interaction and dependence in those models. In order to go down that road, we need to have a bit of a better intuitive understanding of what's so special about Gaussians that make them the things that come up in these kind of renormalized limit theorems. The answer to that, which we'll explore next day, has to do with infinite divisibility.